Welcome you all to the first session of this point set topology tutorial course. As you have seen in the first module, we had started with discussing the norm space, and then went to metric, and then topology, and then function on topological space to topological space. So as a starting point, we start with this norm space. So norm vector space. So in norm vector space, once we have norm, then we can define metric from that norm. And for the norm, we need some of the property satisfied. So first of all, it should be non-negative function. It is a vector space to non-negative maps from a vector space to non-negative real numbers, where the function takes value 0 if and only if the vector is 0 itself. So that's non-negativity of the norm. So these inequality are appear in the checking the triangle inequality for the norm. So for that reason we will discuss these things. So first, can anyone say how to solve the first inequality? You are given this a, b positive numbers, non-negative real numbers, and p, q both is greater than one number, such that it satisfies 1 by p plus 1 by q equal to 1. Then you have to prove that this inequality ab is less equal to a power p by p plus p power q by q. So do anyone have any idea how to prove this one?
We can prove it graphically.
Graphically, okay. How?
I'll take the one function. I'll take y is equal to x power p.
Okay.
And then this AB will represent the area of the matrix, and the right hand side it'll give me the area more than this curve, like more than the area of rectangle.
Yeah, more than the rectangle. Yes, right. So and the other, so that will one way will give you this a power p by p, and exactly the inverse of this y equal to x power p will be x power q. So as suggested. So
Yes.
yes. So let us consider those two functions. So consider this y equal to x power p and as 1 by p plus 1 by q equal to 1. So the inverse of this, inverse of y over x power p will be x equal to y power q. So just verify this. This is just x equal to 1 by y power 1 over p, but y power 1 over p is this 1 minus 1 by q, and from there you can see that this is exactly the inverse of this function is x equal to y power q. Now if I calculate the area under this curve, so now the area of y equal to x power p bounded by x equal to 0 to x equal to a, it is exactly the integration of 0 to a x power p dx, and it is a power p by so there is some error. I need to take p minus 1, right? Yes, so that, okay, yes, so 1 by p minus 1, so that I will get this, right? so 1 by p minus 1 because 1 by okay. Yes, I want a power p by p, so anyway I want this to be a power p x power p minus 1, so that I'll get it a power p by p. And here then the inverse of this will be okay, so x equal to y power 1 by p minus 1, and it is p is just, if I see, so 1 by, so this is p minus 1, so minus 1 will be this, so 1 by this thing will be q minus 1, right? So yes, so okay, so and on the other hand, the area of x equal to y power q minus 1 bounded by y equal to 0 to y equal to b is so it is b power q by q. So how this in graph it look like, so this is the xy plane, and here so suppose this is my some curve, this x power p curve, y equal to x power p minus 1 curve, and then exactly the area, suppose this is my point, suppose this is point A, this is 0, and in this way here suppose something it will be less than or greater than, but I'm in this case to visualize this, I'm assuming this b is less than a. So the total area of this thing, so one way this part a power p by p, this represents this part, so it is, so a power p by p, this is this part, this integration, and the this integration will represent this part, p power q by q. So the total area, if I add just a power p by p plus b power q by q, so this represents this total area. But if I consider AB, so AB will be this rectangular area, this whole rectangular area is, so the extra part is, this part is at least extra. If even if we would have b greater than a, then also you would have this part is extra in that case. So in any way, like in any case, you will get that this rectangular area is q, but it is bounded above by area AB, that is AB is equal to a power p by p plus b power q by q. Okay, so this is just that proof now. So like assuming this one, how do you prove this Holder inequality? we have proved this. Now can someone help me with this, that how to prove Holder's inequality using this thing, Young's inequality? So this 1 by p plus 1 by q is still 1, and this is this thing. So what should I choose, a and b, to get this thing?
I think it's by, I don't remember. Is it by induction?
You can use induction, but okay, let's take simple case. Okay, for n equal to 1, like n equal to 1, it is just the same thing, right? It is just equality, because n equal to 1, it is just x power k power p to the power 1 over p, so that is just x power k, this is just y power k. But
Yes.
induction will be like, can't you do it directly?
No.
Like can you like see something from here, that it is 1 over a power p over p by, so okay, so like this, if you remember this xk, if I can take this, okay, just okay. So 2 is, suppose I take my capital X vector as a vector. If I take x1 x2 up to xn, and suppose I take y to be y1 up to yn, these are two vectors. So I'm assuming my like k is r or n. So in this case you can assume this as both this belongs to k power n, this also belongs to k power n. Now if I defined it my like x by norm x p, so p norm, recall that this norm x p norm, this is just sum of xi power p I equal to 1 to n, this power 1 over p. Similarly, q, if I replace this by q, then it is sum over xi power q to the power 1 over q. So if I now calculate the norm of this thing with p norm, then this is 1, right? Similarly, if I take this thing, so just I'm dividing this part and this part by this xk, and dividing each by xk by this thing is yk by that thing. Okay, so just I'll show for this thing. So this is my xp and yq, this is sum of 1 to n q. Now we need to show, if I just replace this thing, so it is saying sum of mod xi yi I equal to 1 to n, this is less equal to norm p norm and q norm, right? But this is what, this is again the inner, nothing but the inner product of x and y, and like modulus of that thing, not exactly inner product. So okay, just just take this thing. Now this is like to show this, and now you divide those two terms here. Why, when you can divide it if both the norm are non-zero? So let's take that first. So like case 1, either of okay, this side is 0, then norm property will imply that this thing is like has to be 0, or even from this one. So this sum is the finite sum of positive numbers equals 0, then each term has to be 0. So xi all are 0. So left hand side is also 0, right hand side is also 0. So without loss of generality, let p is 0, and then by the norm definition this thing, so this sum of I equal to 1 to n xi power p whole power 1 by p is 0, but that is same as this is 0, but this is sum of non-negative numbers, so that is 0 means individual term is 0. That means xi power p is 0, but this power p is 0 means again this xi has to be 0 for all I equal to 1 to up to n, right? So then let me call it as 1, then LHS of left hand side of 1 equal to 0, and which is same as the right hand side of 1, which is as this is 0, so this is 0. So one's hold in this case. So same we could have assumed this y is 0, the same thing. That's why I choose without loss of generality, I say. Okay, so now suppose that this is none of them is 0. Okay, so case 2, both norm x p this is non-zero and norm y q this is also non-zero. Okay, so don't confuse with this notation, because I'm not saying that this norm x p not equal norm x q, but I'm already saying that this is not equal to 0. Okay, so now I can showing this inequality is same as showing the dividing this thing on the left, right? So thus enough to show one to n this mod xi by norm xp and xq. So this thing is less equal to 1, right? I'm just dividing this part and this part on this side, but sum of that thing is means that you divide this xi by norm xp and yi by norm yq. Okay, this is the same thing. Norm is non-negative, so that's why I put also inside the modulus. So enough to show this, but now look at this thing. So these are like, this is the inner product of two non-negative numbers, right? So take x tilde, this is just this x1 by, so mod of mod x1 by norm xp up to xn by mod xp, and y tilde is y1 by q. Okay, so here the norm of x tilde p, this is nothing but 1, because this is taking the power, pth power, and like it is just dividing by x by norm x, norm x p. So if I calculate the with p norm, this will be 1. Similarly, y tilde with q, this is again 1. Okay, now I'm saying here you like, can you use this Young's inequality?
Yes, sir.
So here I can use, because this is a and I assume this thing is non-zero. So mod of this xi by norm xp and yi by, sorry, this is norm yq. These are like, these are a positive number, because these I assume to be non-zero. So they are if sum xi is 0, that is anyway 0, the total thing. But if sum is non-zero, then it has to be positive. Okay, so this is okay. So here I'll just still yet I haven't used this 1 by p plus 1 by q equal to 1. So I'll use that thing in to use the Young's inequality here. So xi, let's say xk and yk, both are non-zero, then p into yk by norm yq, this thing is less equal to this power p by, okay, so xk power p by this norm power p also, power p into 1 by p, plus 1 by q into this q power q. Now just take the sum on both side. Like if sum is 0, sum xk is not 0 also, then anyway it is 0 equal to 0. So I can take the sum. So 0, then the previous inequality also hold. Also holds. So taking sum over 1 to n, we get this norm xk p and yk by norm yq, k equal to 1 to n. This is less equal to sum 1 over p will come out, so this is 1 to n. This is norm xk power p by norm x p power p and plus 1 over q sum k equal to 1 to n yk power q power q. Now see this sum, just this is a constant norm x p power p, this is constant, this will again come out from the sum. So this is just sum over k equal to 1 to n mod x k power p. So that is by definition again of this norm, this is just norm x p power p, right? So this is same as 1 over p, this is norm x p by norm x, and this is 1 over q, same thing, power q of q. So this is this is just 1 over p plus 1 over q, so this is 1. So that's what we wanted. So again if you just take out from here, so those two constant xp and yp norm, so this is just k equal to 1 to n xk yk is norm xp yq. Case also, and hence we cover the both cases, so the inequality holds in general. So here this thing actually not needed anyway. Okay, this thing is not needed. Just you may start with just the unit norm and show that this is holds for unit norm thing, and then you can simply take that thing. So instead of taking, you can also start with this one, both are same. Okay, so next we have this final needed to show that this p norm that we defined just, so this norm, this is indeed a norm, that means it satisfies the triangle inequality. So to show the triangle inequality we need this, that is precisely the Minkowski inequality, because this is norm of x those two vector x plus y, and this is individual norm of x and y. Okay, so that's the final thing, and here we need this this inequality, Holder's inequality. So third one, so here again x is taken to be x1 x2 xn, y is y1 y2 yn, both belongs to kn. So those can be either real number over real numbers or complex number, in both way they are the same. So here we need to show x plus y, this p norm is less equal to sum k equal to 1 to n xk power p whole power 1 over p. Okay, so this just x plus y is x1 plus y1 x2 plus y2 xn plus yn, that's the sum here. So that we need to show. So let's start with the pth power here. So x plus y, this pth norm power p will be sum over k equal to 1 to n xk plus yk power p, right? Just this 1 over p power will gone to 1. So this thing, now here I want to use this thing. So can someone tell how to use this thing here? How can you use this one? Any idea?
So maybe